Hello again, my name is David Watts and I'm here today with Duncan Furniss from Lenovo in Canada.
Hello,
and I've got Mark here, he's the Senior Thermal Engineer here in the lab. And we're here today in the NeXtScale Thermal Lab here in Lenovo in Morrisville, North Carolina. It's our brand new lab here. And we're going to talk about the new NeXtScale Water Cool system. And we're going to go through these, look at the chassis, the compute nodes, and how it all gets cooled, right?
Yes.
So what have we got here first, Mark?
Well, here's a 6 chassis rack that's got our full 6 racks worth of water-cooled nodes. And here right now we've got Ethernet connected, and we're actually flowing and operating, so we're working under load right now. So we're running an exerciser M prime, so we've got about 28 kilowatts on the whole entire rack right now. And as you can see, we're in the lab environment, so we've got this connected to basically an instrumentation panel. This is what we use to make temperature pressure measurements for a rack environment. And then I have over here a CDU. This is a pretty common CDU that you would see in industry and in customer applications. So here our CDU on the secondary side is feeding my test rack through the instrumentation so we can make measurements and determine the thermal performance of the rack.
And you mentioned that these systems are all fully loaded, right? You're running tests right now that are driving all the processes at full tilt.
Correct.
What's interesting is that we're here in a lab and we're talking, and it's not that noisy, right?
Yes.
Why is that? Why are we able to have a cold conversation with all the systems going full tilt?
Sure, that's a good point. So with the water cooling technology, we are removing system fans. So we don't have the need to have any kind of system fans to move large volumes of airflow. We're utilizing the water cooling components and that technology to cool the processors and other subsystem components. So we can remove those systems that save power and save airflow demands upon the data center.
So Duncan, why would a customer want to have water cool technology? Why would they want to use water rather than air to cool systems?
So there are several reasons for that. One of the main reasons is that the data centers may not be able to remove all of the heat if the machines were being air cooled from the air in the data center. Also, the air handling equipment itself can occupy a lot of space and is very noisy and unpleasant for the data center operators and for the environment.
Right. And of course there's a performance gain too, right?
Yeah, so as the water cooling is more efficient, the water can remove heat much more effectively from the processors and other components in the servers. You can actually run them at harder, and when they're cooled more efficiently, they actually use less power to do their job.
So what the term to do with turbo boost? More opportunity?
So more opportunity to do turbo boost or other performance
and these systems are designed to run processes up to 165 watt TDP, right?
Correct, yes.
So high performing processors are available to this system.
In a very rack dense environment, yes.
Yeah. Now you'll see, as we go through these things, you'll see, by the way, different colors and various other wires and so on. We are in a working development lab. We're in the middle of doing some thermal stress tests, right?
Yes.
So these wires, they're all for your measurements?
Yeah, those are thermocouples. We use those to make temperature measurements. So we're qualifying the thermal components, make sure they're under spec in the operation. That's what the other instrumentation you see that you would not see, in a customer deployment.
Right, yep. All right, so let's go around and have a look at the back, where all the business is for the water.
Sounds good.
Yep. All right, so we're now at the back of the rack, and here are the 6 NeXtScale chassis again. You can see these black rods here, vertical rods, are these are the water manifolds. Mark, what's going on here?
So we have a modular-based manifold design. So as you can see, the hose is coming up, and we're feeding from the bottom in this case. And you'll see that each component is a manifold that goes inside the chassis to make the water connections for each node.
Right, so that's what this is here, right?
That's what the inside looks like.
Okay,
yes.
So walk me through what we have here.
So basically you have a supply tube, and then this would scale out for however many chassis you want.
That's up to 6, right?
That's the beauty of that kind of design. We can be flexible in the number of chassis you want in the rack, and we can basically build that with one part all the way through. And here you'd have the connection to the nodes, and then this is basically to your infrastructure. So water would come in, distribute through the entire chassis for each of the nodes, and you'd have a supply and you'd have a return, or an inlet and an outlet.
So that's what we've got here. This is the inlet, and this is the outlet, right?
Correct.
Yep.
Correct.
So each of these 6 connections here, these go into the back of the compute trays, right?
Correct.
Right, and there are 2 servers in each compute tray, so that's why there are 6, what do you call these nodules?
Connectors.
6 connectors for 12 servers.
Correct.
Right,
Correct.
Okay, yep. And the outlet is the exact same design as this?
Yes.
Yeah, okay.
It's basically just mirrored, yes.
Yeah, all right. So, what else is on the back of the chassis?
So you'll see basically the same air-cooled power supplies that we'd have in an air-cooled chassis. We use that common. And then we have fillers. Again, like we mentioned, we don't have to use system fans to cool the processors of the systems. We are using the water to directly contact the individual components. So now we can remove those 10 system fans from that system and only use the air cooled from the power supply.
Yeah, and it's actually an interesting note that a lot of the components in the water cool solution are the same ones that we use in the air cool solution. So yes, the chassis, if you look at these, the fan bays, those are the same fan bays that are used in the air cooled solution. We just don't need them here. They're the same power supplies as we use in the air cooled solution as well, right?
Agreed. Yep.
Yep.
And same thing with the FPC, the fan controller card.
Yep.
All those items, components are common. We try to build that commonality.
Right. Duncan, what's the FPC all about?
So the FPC is the fan and power controller. So it controls the fan speeds on the power supplies, which actually does some air cooling for some of the smaller, lower heat components in the nodes. And it also manages the power for the chassis, so it can alert on power supply fault conditions, and also monitors the power consumption from the nodes in the system.
And each FPC in the rack has its own Ethernet connection, so you can do remote management through that, right?
Yes, indeed. They are remotely accessible.
Yep. Alrighty. So these chassis and the water-cooled solution are designed to remove 85 to 90% of the heat generated by these systems.
Yes.
So the remaining 10-15% or so, the fans and the power supplies will extract that heat. So most customers will just use that?
Yeah, that's acceptable for a great number of customers.
Yeah.
Yes.
So if a customer does need total heat removal from the chassis and needs a room neutral cooling solution, we have read or heat exchanger,
yes,
right?
we could add a read or heat exchanger to the system and get 100% recovery.
So that's another water solution, another water offering that can work in conjunction with the NeXtScale Water Cool.
Correct. It's not dependent on it. It can work together in concert to give you that room neutral solution.
Yeah, all right. Okay, so let's go back around the front and have a look at each of the compute nodes, shall we?
Let's do that.
Yeah, okay, we're back at the front now. And so we were talking about the water coming in from the into the back of the system. It actually comes in underneath the rack from the CDU and this test rig we have here.
Right.
Now, why is that? Why are we bringing the water in from the front of the server, from the front of the rack, even though all the business at the back?
So this is a feature in terms of safety. If something should happen, if an unlikely event should occur, we would want to be able to shut the water off to the rack quickly. Right. This gives us quick and immediate access to the shutoff connection points.
Right. So these connectors here allow that quick access, quick shutoff.
Correct.
Okay.
And this is how the rack would interface with the customer's infrastructure.
Right. Duncan, you got one of those there, right? So
I do. I have one right here. So they come apart and go together quite easily. These are the flow gates. You can't actually disconnect the couplers when these are open. When you have them both open, there's no restriction to the water flow. And in the event of emergency, you just have to close that and it turns off the water flow. You can close it on both sides. The balls are very close to each other, so there's very little water that can escape when you disconnect them.
So the special feature of these connectors is that when they are open, there's no loss of pressure, right?
Yes, there's no restriction for flow. It's full port.
Yeah.
So in this case, with this kind of connector, you're not paying to pump fluid through a valve.
Right.
Yeah.
Yep. All right, very cool.
And one of the other
Yeah.
features, I think, as well, is that when there is water pressure and the lines are closed, you can still actually disconnect them and connect them very easily.
Yeah.
It's true. With some other connectors, tiles, that becomes a very difficult challenge.
Yeah, okay. All right, very cool. Well, that's the water system. Now let's look at the individual compute nodes, shall we?
Indeed.
All right, so we have, just like the air-cooled system, there are 12 compute nodes in each of the chassis. Two across and 6 up and down. Each pair of servers is actually on a compute tray, and we'll pull one of those out in a moment to show you that. And looking at each of the compute nodes, you can see that from the left here we've got InfiniBand connectors here via an ML2 adapter server.
Yep.
There's also support for a second InfiniBand adapter or other supported networking interfaces.
Oh, right, a Connect IB version, yes.
Yep, yep. And under that is 2 gigabit Ethernet ports, the usual LEDs and power button as well. And then over here is the connector for the KVM cable, right? This is the dongle here, which is gives you keyboard, video, mouse, and serial port access as well. So very similar design to the air-cooled system, right? In fact, it's the same system board, so that's why it's all the same. Yes. All right, so let's pull one of these systems out. Now I would note that this is all running, right? These machines are all running. The water is flowing.
Yes, absolutely. This is running again a very high workload right now. So about 28 kilowatts right now currently with water flowing.
Yeah.
Yes.
So let's pull one out.
It's as simple as just removing the I/O and any connections to the node.
Okay. So if a customer did have a failure, they could do this without any interruption to any service.
Correct. Everything else is running.
Yep.
And then you just actuate the handles and pull the system out.
Right. Yep. Okay. Well, let's take that over to the bench over here and have a look at it.
Okay.
Okay. So here we are. This is the NeXtScale NX360 M5, the water-cooled server. There's actually 2 servers here. This is a compute tray that has 2 servers. They are completely independent, and the system board is actually identical to the air-cooled model as well. So a lot of reuse of similar parts. Of course, the really obvious difference is these copper pipes here. We've got the inlet and the outlet for the water system. Mark, how do these connections all work?
So like you pointed out, we have 2 separate systems. So here the water will flow in and then we split into the 2 systems. And then we attach the cold plates to each of the processors, so we're directly attaching that and we flow through the rest of the system. This way we can cool the processors directly and cool the other components, such as the memory and other system components in the system itself.
So you're saying the water actually does go through all these components. So this is direct water cooled, right?
Direct water cooled.
Are there benefits to running the water directly onto the components?
Yeah, the main benefit is you remove all of the water, the heat at the source that you're generating. You don't have to, for the CPUs, that's the predominant heat source. And so you're going to want to remove the water from that heat source directly. That gives us the most energy efficient solution. That gives us the most capacity to cool any power processor that we're talking about.
Right. And actually I would add too, this water can be warm water, right? This does not have to be chilled water.
That's correct. The only limitation we have for that water is we go from 18 to 45 degrees Celsius.
So the water can be 45 degrees.
45 degrees Celsius.
And there's still enough temperature differential to cool these components.
Absolutely.
Right.
So there's no restriction in terms of that water usage. If you're using a free cooling system where you don't need any chilled water, no chiller plant in the data center, you can use this and utilize the free cooling systems, those systems to dump all the heat from that's being generated and be supported with this processor in the system.
So the copper piping cools the processors and the memory and the adapters up the front. The rest of the components, the small chips in the front, those are cooled by the power supply fans, is that right?
That's correct. We're making use of a little bit of airflow that we have from the power supplies to cool those components.
Right. And of course that's what you've been testing all this time, right? Is testing, evaluating all the temperature settings, making sure that everything remains sufficiently cool.
Correct. We need to make sure that we're within meeting the thermal specs of all the components that we have in the system.
Yeah, okay. Okay, cool. So Duncan, what are the rest of the what's the usual server components in this system?
So these systems have the latest Intel Haswell, the E5-2600 family V3 processors. So we've got 2 processors per system. We've got 16 DIMMs per system. This is DDR4 memory.
So each one of these is one server, right?
Each one of these is one server, yes.
Yeah.
So these are DDR4 memory modules running at 2133 megahertz.
And these are just standard memory DIMMs, right?
Yes, they are.
So what's the cover you pulled off there?
So the cover helps make sure that the DIMMs are actually touching the thermal conductive material.
That's the pink squishy stuff
The
that's
pink
between
squishy
the
stuff,
memory
yes.
DIMMs, right?
That's
Yeah,
Exactly.
that's a technical term, isn't it?
Yes, technical.
Yeah.
And then up front we have the ML2 or mezzanine LOM or LAN on motherboard adapters.
Right, so that's
here.
the ML2 connector there, right?
Right, that
Yep.
would go right in there.
Yep.
The heat pipe would touch this front conductive plate.
Yeah, so they connect. They are physically touching the conducting plate there at the front, right?
Which
Yes, correct.
Yep.
has the cooling water tube connected to it, yes.
Yep.
And then this is the PCI Express Gen 3 full height, half length adapter slot.
Yeah. So these two ones that we've got here are FDR InfiniBand and 40 gig Ethernet, right?
Yes, this is the Connect IB card, and this is the dual port 40 gig Ethernet or FDR InfiniBand ML2 card. The ML2 MESLOM has the added benefit that you can actually talk to the integrated management module through these instead of through the first Ethernet port, if you so desire to use that.
So typical customer that would use the NeXtScale system would use InfiniBand for the interconnect for clustering, right?
Some of them would for systems that need the high bandwidth, low latency interconnect. Other potential customers could just be all connected by Ethernet for highly serial environments, distributed render farms, those kinds of things.
Yep. So this system it's designed to use the high spin processors, 16 DIMM sockets in each server.
Yes.
So 256 gig of memory currently.
Yes.
Very dense environment and very energy efficient, right?
Yes.
Yeah. So ideal for customers that need high compute power and energy efficiency at the same time.
Yes, and very dense compute environment. So you can pack a lot of computing power into a rack. These are up to 36 cores, or up to 72 threads per server. So it's up to 72 cores, 144 processing threads.
Right.
Up to half a terabyte of RAM in one compute tray.
Yeah. And if you look at the system board, you'll see that there are a number of connectors that are not used because this is the air-cooled system board. We don't use some of these components in the water-cooled environment, so those are not used in the environment. Just all right. So let's put it back into the chassis, shall we?
Yes.
Yeah. All right. So there we go. So the server's back in again, and as soon as he plugs it in, the water reconnects automatically. It joins back the water loop, back into the water loop.
It does, yeah.
Power reconnects automatically, and all you did was just plugged in the network connections, and the server boots, and away it goes. Joins the network. Yeah, it's as simple as that.
Yes.
Yep. All right, so there you have it. This is the NeXtScale Water Cool system, Water Cool Technology system. We've got a rack full of servers that are running at full load, 100% load. And yet we were able to talk. We were at the back, and we could still communicate, even though everything was going full tilt. You certainly couldn't do that in an air-cooled system, that's for sure. Yep. All right. Well, thanks very much, Duncan. Thanks very much, Mark. Hope you found the video useful, and we'll see you next time.
All right.